In this video, I'm going to be talking about momentum, momentum that is stored in electric and magnetic fields, and the conservation of momentum when it applies to electrodynamics. So this is in section 8.2.3 in the textbook by Griffiths, 4th edition. And to start our discussion of momentum, we should start with Newton's second law. So Newton's second law can be written as the force is equal to the change in the mechanical momentum with respect to time. Okay, but we already have now from previous lectures a discussion about the work and the force. So what I could do is write down the force as the change in momentum over time, and I could write down now the force in terms of what we know about fields, and I can write it as the surface integral, the closed surface integral, over the Maxwell stress tensor, integrating over the area, minus epsilon naught mu naught, the derivative with respect to time of the Poynting vector integrated over all space, integrated over the volume. So essentially I have two parts. I've got the part with the stress tensor in it, and I've got the part with the Poynting vector. So if we want to get the momentum, we essentially have to integrate both sides with respect to time. So the momentum then would be these two parts. I would get the integral of that stress tensor part, so integrating with over time, minus epsilon naught mu naught, the integral over the volume of the Poynting vector. So now I've got these two parts. One, if you look at it, is a surface term. So we've got the surface term right here, and we have a volume term. We have this volume term right there. So our momentum is basically shared between those two terms, and if we have the same interpretation that we did with energy, then the surface term is the amount of momentum that is escaping the system through the boundary, and the volume term is the amount of momentum that is stored up in the electric and magnetic fields inside the system. So therefore I can write down these two parts. I can write down my momentum of the fields. So that would be epsilon naught mu naught, the integral over the volume of the Poynting vector, and the momentum flux, or the flow of momentum, so that would be the integral of time as well as the integral over the closed surface area of the Maxwell stress tensor. Pretty simple. So two parts, pretty simple equations. Of course, you have to expand out the stress tensor into all of its little pieces, and you have to consider the Poynting vector, which is a combination of electric and magnetic fields. But from an interpretation standpoint, then it's pretty easy. We've got the fields part and we have the boundary part. So the okay, so what we could do is we could just look at the fields part and say epsilon naught and mu naught are constants. We can bring them inside the integral. And then I can call this a new quantity g. I haven't used g before. And so now we just have these two constants of nature times the Poynting vector to give us essentially the momentum density of the fields. So momentum per unit volume. Okay, so we can write this now down in terms of the fields. So I would have epsilon naught, mu naught, and times S, which is epsilon naught, mu naught, E crossed into B divided by mu naught. Mu naughts cancel. And so what I get is that the momentum is the cross product of the momentum density is the cross product of the two fields that we have. So we can now try and write down the conservation rule for momentum. We know momentum is conserved under conditions where there are no external forces. So if there are no external forces, that means that the force equation, the force on the left-hand side is 0. And I can write down now that minus epsilon naught mu naught, the time derivative of this volume integral, plus the integral of the closed surface area, like so. I can now equate these two. So I would have epsilon naught mu naught, the time derivative of the Poynting vector integrated over all space is equal to the integration of the stress tensor over the surface, through the surface, like so. We can clean this up now and say bring the constants are just constants, so we can bring them in front of the on the other side of the integral. We can bring them on the other side of the derivative, and honestly the derivative is we can take the derivative before we integrate over all space. So we could rewrite this now as a volume integral of the derivative of epsilon naught mu naught, the Poynting vector, integrated over the volume. That's just the momentum density. So I have the integral over the volume of the change in the momentum density with respect to time. And now with the right-hand side, we can invoke our good friend the divergence theorem and change that closed surface integral into a volume integral. And so that becomes the volume integral of the divergence of the stress tensor, like so. Okay. Now, that means that whatever's, basically I could combine them together into a conservation law. So that means whatever's inside the integrand is equal to 0. Because if the volume is 0, it would just be a point, and that would be really boring. So instead, the more exciting answer is that we have this equation where these two terms subtracted from each other are equal to 0, or the change in the momentum density is equal to the divergence of our stress tensor. And so that essentially is conservation of momentum now, where these are written in general terms of a momentum density and a stress tensor. So it's only when we assign the momentum density to be something that is related to electric and magnetic fields, or the stress tensor to be made up of something like electric and magnetic fields, that we're applying conservation of momentum to electrodynamics. So the next step you could think is, well, what about angular momentum? We've had conservation of charge, conservation of energy, conservation of linear momentum. What about the angular momentum? And that's not much of an extrapolation, because I could define my angular momentum density, so the angular momentum per volume, as the radial distance crossed into my momentum density. Just like in normal Newtonian mechanics, if I have some moment arm here and I have a momentum, linear momentum, but in this case it's a density, the angular momentum is still just going to be the cross product of those two terms. So that means I can write down the angular momentum density as epsilon naught r crossed into the electric field crossed into the magnetic field. And now I have a relationship for that. So now I can come up with the angular momentum density for electric and magnetic fields, which is pretty interesting. So now if I have electric and magnetic fields in some volume, there is some angular momentum associated with those fields if I'm considering some point that's, far away, and those fields could cause, through conservation of momentum, transfer into rotations. So that's pretty cool. now we can have electromagnetic fields that are not only related to the motion of whatever is going on, but also the angular motion of whatever is going on. So to review, now this is just the quantities that are related with the fields. For the fields themselves, the energy density is 1/2 epsilon naught E squared plus B squared over mu naught. The linear momentum density, we said, was epsilon naught the electric field crossed into the magnetic field, and the angular momentum density is epsilon naught r crossed into the cross product of the electric and magnetic fields. So now we have density, we have energy, momentum, angular momentum, and all of these are for the fields. So this is just the stuff that's stored up because the electric and magnetic fields exist. Those other terms, the second terms in the equation, all of them dealing with the integral over the surface area, are how this energy momentum are now flowing out of the system, or or how it moves around. So we've got the static case of the energy and momentum in the field, and we have the dynamic case of how that energy momentum changes and transfers over time.